welcome back. In the last lecture, we introduced a simple equation, one constant Margulies equation, which satisfies the boundary condition for g axis to be 0 when x approaches towards 0. Okay, and we made a comment that such kind of equation works well if you have binary mixtures like argon, oxygen, benzene, cyclohexane. These are the mixtures, or these are the molecules which have similar size, shape and chemistry. But you have deviation from this kind of characteristic properties or similarity, then you may have to consider more complex relations. Okay, that in other words, more complex equations are needed in order to represent GE of a binary solution. To represent adequately so this is needed if you have problems related to, let's say, because what we are talking about is similar chemistry, size and shape. So any small deviation can affect large, and I will come to this point. I will show you that even the small difference in the size, if they are, let's say, not like 3 times 4 times, but if they are very close by, but still is like 1.2 1.5 times, you might see some kind of deviation from where you need more number of terms. So remember that for one constant Margulies equation, you have only one constant term, this one, and you are trying to characterize all kind of relations with the sizes, chemistries and shape with just one constant. So what is a generic equation which we can come up? So there are many equations which people have developed, okay, and this I can summarize in terms of some kind of flow chart. So now one can consider this expansion of GE in terms of moles and various different component. Okay. Now, as you correlate all these different equations which people have developed, they have a common reason for that, or they are well connected. For example, a generic equation such as GE, which I can write in this way, I can write GE as x1 x2, right? If you have one, then basically it's the one constant, right? But then you can add others plus C and so forth. Okay, it will still satisfy the boundary conditions. Now this will yield your activity coefficient in this way, 1 minus xi square plus bi 1 minus xi cube plus ci 1 minus xi 4 and so forth. Okay, where a are related to this ABC. Okay, for example, a1 is related to a plus 3b plus 5c plus 7d, okay, and so forth. So this is a generic expression which satisfies the boundary condition. And now what, using this, if you consider different kind of approximation, different kind of formalism, or the expression comes up. Okay, so I will just write down this. For example, you can get this Redlich Kester. Okay, you can also get this Wolf, which is more exhaustive, or more, it contains physical interpretation of the system. Okay, and a special case is basically this Redlich Kester. Again, it has expansion of some kind of expansion of GE. Okay, special case. Now using Wolf, we can get Van Laar, okay, and we can get also Scatchard hammer, okay, and Rayleigh's special case is basically nothing but Margulis, okay, Margulis equation. So let me again come to this generic term which we have written here. Now this A, B and C, the number of constants in the generic expression depends on the number of or the kind of complexity of the system which we are going to consider. Okay. So in other words, this number of parameters A, B, C is determined by complexity, quality and quantity of what? Experimental data. Remember, we are trying to fit with the experimental data to get the information between the system. So now what we consider is usually only 2 variables or at most 3 for VLE kind of exercises. Okay. Anything beyond 4 parameters requires extensive experimental data. Okay. Okay. So let me first draw for the Rayleigh-Kister. So Rayleigh-Kister expression from here. Okay, this is the generic expression. So what I can do is basically, instead of writing this without solving the expression, I am going to write down the generic expression of Rayleigh-Kister. It's RT ln gamma 1 by gamma 2 is nothing but RT ln gamma 1 minus RT ln gamma 2, and from here you can do the mathematics, rearrange everything, and so that we can avoid here, and I can simply write this expression as see, the point is that these are the expressions which are a little complicated, and thus you do not have to remember this, but having an understanding of what was the origin of this at least appreciates little more than simply giving you or using this just like standalone expressions. So now you have these expressions just to give an idea what this A, B, C contributes. What I am going to do is I am going to draw A is equal to B is equal to C for the case of this where we consider equal values. All right. So just to give you that how different these different groups or the component of this expression contributes to the G of E. So this is, let us say, 0, okay, and you have x, one of the variable x. So I am just going to draw it that for the case of A, B, C equal to 1, this is how it is looking like for the case of A.
So with respect to x.
yeah, with respect to x here, and this is the one for B, and this is okay. See, okay, it's not perfect the way the experimental data would be, but just to give you an idea that these contributions are non-trivial. Okay. Now, as far as this is concerned, this Redlich cluster is concerned, it's a convenient method to represent liquid phase. Phase gamma. Okay. Now, note that if I had consider B is equal to C is equal to D equal to 0, because there could be other terms also, okay, then ln gamma 1 by gamma 2 would be simply A times x2 minus x1, okay, and it is a straight line. So, for simple system where you have a similar size, the way we have used for one constant Margulies equation, you can also use the same way for similar systems such as toluene, hexane, benzene, isooctane. Okay. For the case of this is a similar size. Okay. So, it works well. For the case of this is dissimilar size. So, it does not work, and thus here in this case you need more terms. So, in other words, one thing which is clear to you should be that if you have the data of the experiment, then you should be able to derive or calculate the activity coefficients as a function of composition. Okay. So, so experimentally one can determine gamma 1 and gamma 2 as a function of x. Okay. Usually this expression should be at constant temperature. What you have seen here, this is supposed to be at constant T, but in practice the temperature is varying, and thus we consider that it is valid. In the other thing is usually the experiments are conducted at constant pressure. So, what we assume in this case, assume that T does not change over the composition much, because of course there will be small changes in the temperature over composition. Okay. Now, let me just give you a flavor of this again ABC for different kind of systems. Okay. And how does it look like if you plot this ln gamma 1 gamma 2. So, again this is x1 gamma 1 gamma 2 . Okay. Now, this is a case of hexane, toluene. Okay. So, in this case, as we said that we can consider B, C, D is equal to 0. Okay. And this log gamma 1 gamma 2 will be a straight line, and it's beautifully the data, if whatever the data is in the experiment, beautifully falls along it, which clearly tells you that it's a good approximation, because one data is able to fit where A by RT is 0.352. If you want to understand the sizes, if sigma represents the sizes, then it's approximately 1.23. Okay, so effectively they're almost close to each other. Now, if you consider, as I said, the benzene and isooctane, I said these are not good enough because these are dissimilar size. All right, because the ratio of the sigma is around 1.86. So, in this case, let's look at how the data looks like. Okay, so again here C is equal to D is equal to 0. Okay, so I'm going to consider B also in this case. There's two parameters. So it is something like this. Okay, and the data are pretty good, pretty much well fitted to these things. Again, this is X1. So this is your benzene isooctane, where we have considered two constants here, and so this is a low complexity. This will be intermediate complexity, right? And remember, these are non-polar. Still, we are not talking about hydrogen bond. We are not talking about anything like that, right? So it's still an intermediate complexity where only the size can create such kind of complexity. So here, if you look at A by RT, it turns out to be 0.433. B by RT is equal to 0.104, and this data is some pressure range. Okay, it's not at constant, so some pressure is varying here. Okay, and sigma difference in size is 1.86. Okay, so if you want to fit this using this, of course you can clearly see that this is not going to be well fitted. So you need to include second constant here. Now let's look at little more complications where you have hydrogen bond also. Okay, so I will consider the case of ethanol and methyl cyclohexane. Okay, so here you have this ln gamma 1 by gamma 2 x1. Okay, so it's a complex shape and as well as the hydrogen bond, methyl cyclohexane, complex shape and as well as the hydrogen bond. In this case, you need 4 parameters, and the way the data looks like is this. Okay, so there's 4 parameters. So in this case, A, B, C, D are non-zero. Okay, and of course degree of hydrogen bond depends on the concentration. The values may have more effect on it. More or less, the message here was that the number of terms in the expressions of Gx clearly depends on the molecular nature of the systems. Okay, so you cannot randomly just choose anything. You have to understand the nature also in order to come up with the right kind of terms in the system. So now you can clearly see right here that this kind of expression, Redlich-Kester, is coming directly from here, and from here you can get a Margulis kind of equation also. Now we look at Wolff expressions. Okay. So let's describe Wolff's expression. Yeah, so this is a general expression again. Which can be systematically expandable for multiple component system. Okay, so I will first let me just write it down and try to give an idea that why this is a very profound expression. See, the expression looks like this. And it may look like to you very arbitrary, but there is a sound reason for all this term, and I will just come back to that and explain you that. And so forth. Okay. So what this Wolf did is basically it tried to explain or give a physical significance to model parameter. Remember this earlier? We talked about ABCD. It's a function of temperature, more or less. But effectively it doesn't capture the typical sizes of the molecule, and we know that the number of parameters which we require depends on the dissimilarity of the sizes, shapes, and other chemistry. So what Wolf tried is basically bring that some kind of physical representation of the system. So what it did is that it expressed the Gibbs free energy of a binary solution as a power series in Z, okay, which is the effective volume fraction of each component. So what is a Z? So we are considering only binary component here, right? Okay, where Qi, so this is the effective volume fraction of the component. What is Qi? Qi is effective volume, or so this would be nothing but cross section of or sectional or sphere of influence, right? Because defining exactly the molecular size, so we are trying to make use of that concept. So this is effective volume of, let us say, molecule I. Okay. So if you look at the expression, this expression is nothing on the right hand side. If you look at it, this is effectively as a function of Z, which is nothing but the volume fraction of each component. So this is, look at, this is a volume fraction. It's like a weighted volume fraction, right? Now let me just spend a bit more time here. This is the effective one, and if you are a bit concerned that where these terms comes into, why there is a 2 here, why there is a 3 here, let us look at it. This is basically, you assume that your system is filled with 2 types of particles, one is 1, other is 2. Now A is basically Aij is nothing but interaction coefficient, which one can model as virial coefficient. Okay. So let's ask this question: what is A12? This is going to be a constant, okay, constant which is basically nothing but a characteristic of interaction energy between molecule of type 1 and one of type 2, okay, and A112 would be, so A12 is basically simply between 1 and 2. Now A112 means there are 2 of type 1 and 1 of type 2. So that is the effective interaction between them. So this will be a constant characteristic of interaction energy between 2 1s and 1 2, okay, right. So this number, the prefix of this 2 comes from this combinatorial factors. So, for example, if you look at it here, A12 multiplied by Z1 Z2 effective volume fractions, this plus A21 Z2 Z1, this is considered to be same, and that's why you have A12 Z1 Z2. Okay. Similarly, we can consider 112 Z1 square. There are 2 of type 1, 1 of type 2, and this is Z2 plus A121 Z1 Z2 Z1 plus A211 Z2 Z1 square. So, this is basically 3 combination we have for having 2 of type 1 and 1 of type 2, and if you come up with different combination, this is the way you want to write it, and these are going to be all same Z1 square Z2. Okay. Similarly, you can come up with other terms. So these numbers which you are getting is basically coming from the combinatorial approach. 2A12 Z1 square, 3 A112 Z1 Z2 square. Now, if you consider 2 of type 2 and 1 of type 2, you will be having the same prefix 3, and it will be Z1 Z2 square. If you have 4 of type, 4 particles, 3 of type 1 and 2 of type 2, you can show this to be like this. So this is the idea. This is how Wolff have come up with the expansion of GE in terms of the effective volume fractions of molecules. Okay, it will continue. So this is the expansion we are considering. That's how what we are doing is in a similar way virial coefficient works. Why the virial coefficients are there? If you look at the carefully, B stand for 2 particle, C stand for 3 particle, D stand for 4 particles. So D represent the intra-effective virial coefficient of having 4 particle contribution to the equation of state, right. So similarly here the similar concept has been used where this different groups of particles of different combination contributes to the excess free energy, gives excess free energy, right, in the same form. Of course, the question is how far we would like to go, and practically we cannot go beyond certain range. So that's what different possible models we have to consider. Now, one model suggests that if you can simply consider, let us say for binary mixture Q1 Q2 simply is molar volume ratios, because what is Q? Q is effective volume. So if you just consider molar volume, that is one approximation we can consider. So let me just elaborate more on this. Now note that in that expression which I have written, it goes to 0 as x1 or x2 goes to 0, which essentially means that this general expression of Wolff is basically considering the ideality in the Raoult's law sense. Okay. So now if you would like to consider Gx in terms of the Henry's law, then you have to come up with the different expressions. Okay. So when you consider the Henry's law, then we will be writing something like this. So if Gx is taken relative to an ideal dilute solution for component 2, okay, then we will going to write like this: star RT x1 q1 x2 q2, and the right hand side is little different. Any idea why this is different? So okay, any idea why I am not considering other combination? So Gxs, right? So it's already dilute in component 2. Okay, so it's a dilute solution. So any deviation is due to the interaction between 2, not between 1, or 1, 2. So this is why because the excess, right? So any deviation is basically due to the interactions between that 2 particles. So in a said reference is dilute in species 2 That means interaction among species 2 molecules are responsible for deviation from ideality. Okay. So, in this case you are going to consider for x2 equal to 0, gx putting star is going to 0 and x1 goes to 0, gx is not equal to 0, because when this appear the other one gx will be 0, but not this one, right. Okay, so that was the idea behind introducing Wolf. I will take in the next lecture examples of spatial consideration for getting Van Laer equations, okay, and the other one Scatchard-Hammer's equations. Okay, so I'll stop here. I'll see you in the next lecture.